So before the break, we were talking about centripetal force, and we talked about bank curves, which we just did a bank curve problem. And we talked about unbanked curves. Okay, we talked about a number of different situations involving uniform circular motion and centripetal force. Okay, so as we were saying, one of those situations is the unbanked curve. Right. So this problem here is an unbanked curve problem. What force acts as a centripetal force in an unbanked curve? Friction. Okay, friction is what keeps you from sliding out of that corner. Right? And when it gets icy, like it did on the weekend, if we take corners too fast, then we slide in a straight line because friction is not providing enough centripetal force to make us turn.
You could like even stay on a road of friction.
Well, if there was no friction at all and it was banked, there's only one. Yeah, this is unbanked. Okay, so in a bank curve, yeah, the bank keeps us in the corner, right? If we go, but I mean, if it was perfectly frictionless, you would have to go exactly the right speed. The chances of that are like nil. That you'd have something perfectly frictionless are nil as well. So, all right. So what we want to look at here is determine the maximum speed at which this car, which is 1,500 kilograms, can negotiate this curve that has a radius of 40 meters if the coefficient of friction is 0.6. All right. So we already know that friction is what keeps me in the corner. So that means that the centripetal force is being provided by the force of friction. And as we said, that's going to be kind of the challenging part of this unit, is always determining what is Fc equal to, okay? What force is providing it in this case. So once I get to this point, then I can put in the formulas. The formula for Fc is mv squared over r, okay? And the formula for force of friction is mu times the normal force, which on a level surface is equal to m times g. All right, so really what we've done here is the sum of all forces. Friction is the force that's acting into the center, so it's the sum. Okay. So I want to calculate V. What do I have to do with R? Multiply both sides by it. Okay, so R is gone. What happens to the M's? Yeah, they cancel out because I would divide it over, right? And then I have to square root. So V is going to be the square root of Muger. Okay. All right, when I plug in my numbers here, that's the square root of 0.6 times 9.81 times the radius, which was 40. Okay, so our maximum speed going around that corner is 15 meters per second. We only have two significant figures in this one. Hey, is that ringing a bell? Okay. So today we're going to spend kind of looking at different situations where, you know, what force is providing Fc, doing a little bit of problem solving to do with uniform stuff. Okay, and then tomorrow we'll be looking at more application type stuff, and then Friday we're doing another lab. Okay, on but it'll be the same as what we did yesterday, except we'll be changing the centripetal force this time and testing its effect on speed. So that's kind of where we're headed. Also, probably this week we will finalize the date for West Edmonton Mall and get you your permission forms so that you can get them home and signed and all of that kind of stuff, okay? Because that'll be coming up. May 6th. You asked me what day is May 6th. I said May 6th.
What day of the week is it?
It's a Monday.
Next Monday.
It's Monday, yeah. I'm just being a smart aleck, sorry. Yeah. Okay, I want you guys to try. Let's go with 1 and 2 for right now, okay? I'll make them bigger so you can actually see them. And we can all leave out the obvious joke here in that there are no Edmonton Oilers skating right now. Yes, we all know that. Yes, us Oiler fans are sad. But we're sad all the time, so we deal with it. All right, so for number 2 here, okay, we know that the radius of the circle they're using to test this prototype car is 100 meters, okay, and that the mass of the car is 1,200 kilograms. Okay, and it's tested and found to skid at a speed of 95 kilometers per hour. What do I have to do with that number? Change it to meters per second. Okay, it's not going to work in there as 95, so I've got to go 95 divided by 3.6. Okay, so now I've got my speed in meters per second, 26.3. Okay, meters per second. Now I can find the coefficient of static friction, okay, between the tires and the track. So I've got mv squared over r, my FC, equals mu times the normal force, which is equal to gravity. Okay, so I'm just looking for mu here. M will cancel, okay, and I've got v squared over rg. Now, what do you notice about that? Does that same manipulation show up anywhere else? V squared over rg? Okay, it's almost like these curves have something in common. Okay, it's that they do. Whatever's holding you in the curve is dependent on V, R, and G in the same way. Okay, whether it's the coefficient of friction or whether it's the angle of bank, okay, they affect that thing in the same way. All right, so if we're solving for this here, then we'll have our 26.388 squared, okay, divided by 1,200 times 100, okay, and sorry, not 1,200 times 100, 9.81 times 100. Okay, and that should give us our 0.710 as our coefficient of friction. Okay. What's that? How'd you do it? It may not have ended up being as different as you think, right? Like if you found the acceleration produced by each one of these forces, which is I think maybe where you went, then yeah, you would have got bigger numbers. But in the end, because mass didn't matter, okay, what we really had over here was v squared over r, which is how we calculate acceleration. Yeah. Okay, I don't think we need to do number 3 because we've already done a few like that. All right, so I'm going to put the sheet up here, and I want you to try a bunch off of the sheet. Okay, there's different kinds on there, a little bit different contexts than what we've been dealing with, just so you get a kind of a feel for it, and then we'll start looking at kind of different applications here. Okay, so number 8 is a generation gap question. Although your guys' generation is now starting to see vinyl return. Okay, you're seeing the return of something that makes no sense whatsoever that it should come back. It's completely impractical. Okay, like you have to be sitting at home on a steady surface for a phonograph to work, right? A record player that spins around and around. All right, so we want to calculate the speed and the acceleration of a point on the circumference of an old style phonograph that revolves at 33 1/3 revolutions per minute. Okay, what did they just give me there? Frequency, right? So my frequency is 33.3 repeating, okay, hertz, or sorry, not hertz, revolutions per minute. Okay, the diameter of the record is 30 centimeters. Do we ever use diameter? No, so we want radius, 0.15 meters. So there's a couple of just contextual tricks in the question. Okay, so we're looking for speed. So remembering that v equals 2 pi r over t can also be written as 2 times pi times r times f. Remember, f is 1 over t. Okay, so we can also write that formula that way. Right. The only thing I would do is that I would change this to revolutions per second. Right. So divide that by 60. So I got 33 and 1/3. All right, so there's our revolutions per second. Now that we have that, now we can plug it into that formula there. Okay, so we'll have 2 times pi times 0.15, our radius, times our answer, okay, the frequency, and then we get 0.524 meters per second. okay, as our speed. And then to calculate our acceleration, remember that centripetal acceleration is v squared over r. Right? We just calculated what v is, so we can use that answer now. Okay, so we'll take that, right, and we'll square it. Whoop, not that, square it, and divide it by the radius, which was 0.15. Right, and we get 1.83 meters per second squared as our centripetal acceleration. All right. Any other ones giving us trouble? Okay. I'll give you guys about a 5-minute break here. Okay, take a little break, and then we're going to talk about some other applications here when we come back. Okay, so uniform circular motion is used for obviously, bank curves, unbanked curves. We talked about those already. But there's some other problems that it could be applied to, and that we do use it for. Okay, we use it in certain types of amusement park rides and things like that to give people a sensation of, of G-force and things like that. But it can also be applied if we're talking about problems associated with making a journey from Earth to somewhere else. Okay, there's a lot of health hazards involved in being an astronaut. Okay, you got much greater exposure to radiation. Okay, being outside the Earth's atmosphere, where you're no longer protected by the Earth's magnetic field, things like that, means you get a much higher dose of radiation than someone staying on Earth would. So you've got the higher risks of different types of cancer and things like that. Okay, there's certainly that risk, but one of the biggest health problems associated with being an astronaut is the effect of weightlessness on the human body. It is not good for you to be weightless. Okay, your body evolved in a weight environment, okay, in a gravity environment, and much of how our body works is dependent on gravity. Okay. So this is actually where Chris Hadfield's research is kind of all involved, or where he did his research, was the effect of weightlessness on the human body. And what they found is there's a number of really big problems with being weightless. Okay, some of them are neuro, okay, or sensory, and others are like honestly physiological or physical types of issues. The first ones that people notice are the sensory ones. How do we balance? What? Yeah, it's the stuff in your ears, right? In the little semicircular canals in your ears. Like you turn your head, and the little hair cells get, well, they're called hair cells. They're not really hair, but okay. You tilt your head, gravity pulls them this way, and tells your brain the head is tilting, the body is leaning, tense the muscles on the other side so we don't fall down. Okay, and it just happens automatically, and we don't ever think about it. You get into space, and that organ goes ape. Okay, like it's like the car alarm that just keeps going off and won't shut off. Okay, it's that horn that's constantly beeping because it's constantly telling the brain, we're upside down, we're right side up, we're leaning, we're falling, we're upside down, we're standing, no, we're not. And it just keeps sending them all these bogus messages that aren't true because it's confused. Gravity's no longer there to tell it which way is up and down. So just like we do, okay, with that car alarm, we eventually just ignore it. Okay, and so eventually your brain just says, man, that guy is crazy, and I'm not going to listen to him anymore, right? And so it just shuts off the messages from the balance center in the middle ear. What does it rely on instead? Your eyes, which is fine. Okay, it can rely on your eyes. It takes a couple of days for astronauts to get used to doing that. The first few days in space are very unpleasant for most astronauts because they're quite nauseous. Okay, getting that switch over from the regular balance center to using the eyes as a cue for which way is up and down takes a little while, right? But once they do that, they're fine in the zero gravity environment. The problem comes when you return to a gravity environment. Now relying on your eyes is a problem, because when you turn, what does your body say? You're falling. Yeah, you're tilting, you're falling, something's wrong, you're relying on your eyes are looking over there, your eyes are looking down, we're falling. Okay, and then your body sends the messages to correct that, but they're wrong, and you fall. Okay, and you look really, really stupid. Right? So if you've ever seen what these guys look like, when they come back, you don't see a lot of footage of astronauts when they first arrive back on Earth, because they're basically escorted everywhere, because they look drunk when they come back. Okay, so when they're walking them, from the, the landing area, they're coming down the, the stairs. When they used to have the space shuttle, they'd come down off the stairs. They would have like this white knuckle grip on the railings, okay, coming down the stairs, because when they look down the stairs, they want to fall because their body would tell them they weren't oriented correctly because it's still relying on the eyes. It takes a little while for the brain to go back to the middle ear for balance. So you imagine you fly all the way to Mars. You're going to be the Neil Armstrong of Mars. You are going to be the guy that gets to make the first step on another planet. Okay, you're standing at the top of the stairs. You've been in zero gravity for 8 months. Okay, you have this whole speech planned. You look down the stairs and down you go, and you leave the first faceplate print on the surface of another planet instead of a nice boot print, okay? And your first words are, "Oh crap," instead of some nice philosophical thing like you thought you were going to say, okay? So there's some issues sensory wise with being in zero gravity and returning to gravity, okay? The physiological problems are the real problems, okay? Once weight is gone, your body starts to recycle the things it's not using, your bones and your muscles. Okay? If you're not constantly battering your bones by walking, lifting stuff, doing whatever, having impact, they'll start to weaken. This is why they usually tell elderly people you need to do a lot of walking, you need to do more load-bearing exercises and things like that, because they need to strengthen their bones. They need to make them more dense, because as they age and are less active, their bones become less dense and they get osteoporosis. Okay, you guys heard that term before? Okay, so they tell them do these weight-bearing exercises, walk more often, and their bones get more dense as a result. Okay, well, if you're in zero gravity, even if you're a healthy person, there really isn't a way for you to do that, and so your body starts to pull calcium out of your muscles, out of your bones, and they get less dense. Okay, in fact, when Chris Hadfield returned to Earth after his stint on the International Space Station, his bone density was the equivalent of someone who was about 60. Okay, because he'd been in space for a long time, and there's just not any way to really simulate otherwise, okay, the impact that you would normally experience on Earth. The other problem is muscle mass. Okay, if you're weightless, you're not, everything is easier to move. Okay, you're not lifting weights, you're not picking things up all the time like you normally are. Your legs aren't constantly bearing the weight of the rest of your body while you walk, so your muscles atrophy. Okay, it would be the same as if somebody, got all jacked up, they were on, working out all the time, and then one day they just quit. Okay, they quit working out, and all they did was sit on the couch for the next 6 months. Okay, all of that muscle is just going to get recycled by our body. Okay, the muscles will atrophy, and that person will get weaker and weaker, and that happens to astronauts as well. That can be a real issue when we're talking about the heart, and we're talking about the breathing muscles. Okay? This happened to some Soviet astronauts. When the Soviet Union crumbled, they still had astronauts on their space station. They didn't have the money to go get them, and they wouldn't let anybody else go get them either. Okay, like the Americans said, hey, no problem, we'll go up and we'll get them because we want to take a look at your space station that you wouldn't let us have a look at, right? And the Russians are like, no way, man, you're not going up there. Okay, you don't get to look at our stuff. Okay, you can send them food and water, but you can't go up there and get them. So these guys were stuck up there for a really long time. When they returned to Earth, they almost died because the muscles in their rib cage that are responsible for ventilating your lungs, okay, like when you breathe in, right, your chest expands. Okay, there's muscles that cause your chest to pull upwards and outwards and cause you to inhale. Those muscles on those astronauts had atrophied to the point where they couldn't lift their rib cage in a gravity environment. They nearly suffocated. They had to be put on supplemental oxygen for a week, okay, in order for them to rebuild the musculature that allowed them to breathe. Okay, they had to basically be completely inactive because their heart muscle had deteriorated. It was suddenly trying to pump heavy blood when the blood was weightless before. Okay, trying to pump that to the brain, okay, was really hard because the heart had just atrophied. Okay, so gravity, or being in a zero gravity environment, is very, very hard on the body. Okay, so for those reasons, we got to watch out for those kind of health risks. The deterioration of bones can lead to the development of kidney stones. Okay, anyone ever had a kidney stone? They're exquisitely painful. Okay, if you ever have to pass one, okay, imagine peeing out a really sharp little rock. Okay, that's what a kidney stone is. You have to pee out a little rock, and it's really sharp on all edges. And when it's coming out, it can cut up your urinary tract, which can cause urinary tract infections, which on Earth aren't a big deal. You go get some antibiotics and you get better. You're 8 months from Earth in space, kind of a bigger deal. Okay, if you get an infection out there, it could be deadly. Okay, getting a kidney stone that you can't pass, that's lodged and would require surgery to remove, and sometimes that happens. That's a pretty big health concern, right? So all of these things can happen, and there are things that we have to start thinking about if we want to send people great distances.
Like International Space Station, why don't they just have like a big center?
Well, the problem with making those things like you've seen in all the science fiction movies is they work great in theory, but in practice, they always add an angular momentum to the ship, which causes the ship to want to turn all the time. So it's not as perfect as what it makes it look. Oh, we'll just put a centrifuge on the ship and then there can be gravity. That's all well and good, but actually building one of those is a lot harder than knowing that it would work. Okay, and that's what we're going to talk about, is how that centrifuge can create artificial gravity, okay, and kind of be a solution. We just have to figure out how to make it work. Yes, and they do have some of that. In fact, astronauts spend several hours a day exercising now on the International Space Station. They have a special bike, a special treadmill, and something that's like a Bowflex. Okay, because taking weight up to the International Space Station doesn't do any good, right? First, it's really expensive, and secondly, you can just move it around, right? Put the big, put all the plates on the bar, and then whoa, off you go, because you can't stop. Gravity doesn't stop it for you. Okay, so you'd look silly, but obviously weight doesn't work. So they have a Bowflex-like resistance machine. All right, we'll talk more about that. Start a class tomorrow.